So you'll hear both of these terms, positive sequence, negative sequence. Sometimes they call this ABC sequence. This is CBA. So as you're doing the homework assignments, we have an ABC sequence or a positive sequence. What that means when they say positive sequence, if VAN has a value we call V maximum angle theta, then VBN is going to be the same maximum value, and the angle is going to be subtracted 120 from it, theta minus 120. And VCN will be Vmax, the same magnitude, the angle will be negative 240. The negative sequence is the angle is backward. If VAN equals Vmax angle theta, then VBN will be Vmax angle theta plus 120, and VCN will be Vmax angle theta plus 240. The other thing you will find out, if you know VAN, then you can find VBN. We said VBN is going to be the square root of 3 times the maximum value, and the angle you'll subtract from it what? I mean, you'll add to it, not subtract, I'm sorry. Add to it 30 degrees. These are all degrees. And VCN, oh, VAB, that's what I meant to say. What did I write?
VBN.
I wrote VBN. VAB. The line voltage. I'm still trying to figure out what's wrong with the camera. This is VAB. VBC is going to be this one, except now you're going to subtract from it 120. So whatever this one, subtract 120 from it, that will make it theta what? Plus 30 minus 120, which is what? Theta minus 90 degrees. And the next one, VCA, is going to be the square root of 3 VM, and you subtract another 120 from this. What's negative 90 minus 120? Is it negative 210? For negative sequence, VAB, very similar to this, but instead of adding 30 degrees, what do? Subtract 30 degrees. And VBC is the square root of 3 VM, and this will be whatever this angle. Remember, this is 120 degrees off phase plus 120. You add to it 120 because each one plus 120 more. See them? So when you add 120 to that, that will make it what? Plus 90 degrees. And the next one, you add another 120 to it. Theta plus, what's that, 210? So I just meant to write these last time. We talked about positive sequence, negative sequence. I didn't really summarize them. We looked at the book there. It talks about positive sequence, ABC phase sequence, or negative sequence, which is CBA, right here. And it talks about VAB is going to be the square root of 3 VP. That's the peak voltage, the maximum voltage, angle 30. That's if we make the assumption VAN has an angle of 0. Theta is 0. If theta is not 0, these will change a little bit. So the equation I'm giving you as a rule there, you know. And we started doing last time Y to Y connection. We went through that. We did a couple of examples with it. So today we're going to do the delta connection. That means delta to delta. So this is the y to y here from last class. So now let's do the delta connection. Which is delta. We use a triangle connection. Where we're going to have a problem is, well, not a problem, but when you have a y source and delta connection, that's where you have a problem, you know? What do I mean by having a problem? Let's take one, just to show you what I'm talking about. This is the y source. And if I do delta now, load, and you make this A, B, and C, when you attach A to A here, and B to B, and C to C, the problem here is that current going in, I sub AA here, from here to there, does not equal this current. That's a node. So you got to find what that current is. If I label that way, and I label this, for example, this way, I sub AC, this current equals this plus that. Where Y to Y, this was the same one going through the load. Here is going to split. So it makes it a little bit challenging there. So we have a couple of options in a case like this. We can either convert this to a delta source, or we can convert this to a Y load. So you'll have Y to Y or delta to delta. Because if you have delta to delta, you'll see the voltage source will be in parallel with these, and just use Ohm's law, or Y to Y. I can convert this actually to a delta source. How would I do that? That's where these equations come in handy. I can replace that Y source with this source where VAB is this value, VBC is that value, and VCA is this value. And that will take this source and make it look like this.
Can we do something really similar last in circuits 1 with resistors? We took the resistors going in at a point like that and then turned it into a delta.
I know what you're talking about. From last semester?
Yeah.
Yep. I saved that sheet intentionally. The question here for people on the video. Yep, the question is, last semester in circuits 1, we convert from delta to Y and Y to delta. I says, what do you know? I saved that from last semester. And we can still use that, except instead of R1, R2, is going to be what? Z1, Z2, and Z3. ZY, ZX, and ZZ, whatever you want to call it. So we still can use this, delta to Y and Y to delta, absolutely. I can take my load and convert that. So I'll keep this handy. And let's take an example. I'll find one, we'll go through it. Where's delta to delta? Well, this is actually a short one here. And I'll mix and match. It says determine the amplitude the amplitude, that means just the value of it, of the line current in a three-phase system with the line voltage of 300 volts and supplies $1,200 of power to a delta connected load. And we know the power factor at a lagging power factor of 0.8. And after you finish with that, since you're having fun, then find the phase impedance of the load. What I know is we have a load here. I can draw the load of delta like this. This is A, B, C. Okay. We have a line voltage of 300 volts. The voltage here is 300 volts. The load here absorbed 1,200 watts. Each one of these is going to take how much? Each one. 400 watts each. Power factor is 0.8. So we can calculate what we call per phase for each one of these. We can calculate what that current is. That current, let's call it AB here so you'll know. Can we figure what that current?
Power is voltage times.
Okay, that's average power, good. So that's 400 average power equals, assuming these are RMS values, which they are, RMS, IRMS, cosine theta V theta I, or power factor, right? So 400, we know the voltage here is 300 volts. We're not sure what that current, we'll call it IAB, times the power factor, which is what, 0.8? Can we get what that current equal to? Okay, that would be 400 times 0.8, 320, so what did I do that for? 400 divided by 300 divided by 0.8. 1.667. That's the magnitude of it. No angle. I can give the angle, by the way. If theta V has an angle of 0, we know what the power factor,
Negative.
lagging, so theta V minus theta I will be a positive value. But the question is find the amplitude. So they don't care about the angle. They want the value of the line current. What is the line current? They're talking about the current coming from the source, from here, from A. What is that current going that direction? This current is going to come split this way and that way. And the magnitude of that current, I sub AA, is going to be the square root of 3 times that number per phase. It's always going to be the square root of 3 times that number. Where is it? That's the voltage, so is the current. So it's going to be this, and you can do actually, you can find the current through each one of them, you know, because we can find the current through that using the same equation and just do the math. It's going, the current in I sub A equals I sub AB plus I sub AC, and do it that way. But it's going to be the square root of 3 times 1.667 2.87. That's the answer to the first question. What is the magnitude, the amplitude of the line current in a three-phase system with the line voltage of 300 volts and the power is 1200 watts to the load?
What do you mean by we could find the current from A to C and then just do A?
You can find, yeah,
AC.
KCL at this node.
Wouldn't it be the same thing as the other current, or am I getting that confused? Because we don't know the VRMS across.
Well, it would be a
AC.
phase shift, a phase difference
Right.
of 120 degrees here,
Or-
120 degrees there.
Yeah.
So the magnitude will be the same, but the phase will be different. So that's why that number becomes the square root of 3.
Got it. Okay.
So instead of finding the angles of all of them, we can just.
Yep, square
Just do square
root of 3, yep. And the reason, actually, watch this, mathematic, or let me finish this and I'll come back to that one. I'll just show you the math there. Now the next one is, can we find what the Z value is? Well, that means I really need to know what we have there. Z is the voltage divided by the current. Right? The voltage over the current. What is the current through this and what's the voltage here? So Ohm's law says Z equals V over what? I. What is the voltage here?
300.
300, and what's the angle? We're not sure. We have no idea. We call it theta V. Right? And what's the current? The current through this one, A to B.
1.667.
1.667, some angle we'll call theta I. Right?
Mm-hmm.
What's 300 divided by 1.667? 180 roughly?
Yeah, 180.
180, and what's the angle? Don't you subtract theta V minus theta I? Wait a minute. I know what that is. That looks familiar. What's the power factor? Isn't that cosine theta V minus theta I?
Mm-hmm. We have.
And my power factor is 0.8. And we take the inverse cosine of 0.8. And is that 37 degrees? Second cosine of 0.8, 36.9, right?
Do you have to change your calculator from degrees to radians to do that?
Well, they're always given degree mode here.
Oh, okay. I
So
didn't do the.
theta V minus theta I is approximately
There it is.
37 degrees.
I did cosine
Yeah.
of 0.8.
Yep, inverse cosine. 37 degrees. So do we know what z equal to? Remember, it's log and has to be positive angle. 180, 37 degrees. We can break it down to real and imaginary and tell if you have a capacitor or inductor. Well, the fact the power factor is lagging, that's an inductor. The J value will be positive. Why? What angle you're in? 37 degrees here. The imaginary value here, that's the imaginary, is positive value. And that's the real portion. So it's going to be an inductor. If it was a leading power factor, the angle in the fourth quadrant, the imaginary value would be below the x-axis, which is a negative number.
Yeah,
And that's capacitor. Yeah. But that's the end of this problem.
We say it's
Z is 180, 37 degrees. Now if you want to break it down, that's 180 cosine 37 plus J 180 sine 37. So 180 cosine 37 is 143 points, how about 144 roughly? What's 180 sine 37? 108. So it has a resistor of a value of 144 and an inductor of a value of 108, J 108. So that's a resistor and an inductor. And if I know what the frequency is, because remember this value is equal to J omega L, right? If I know what that frequency is, if it's 60 hertz in the US, then I'll divide by 377. So if I want to find what the value of L is, I go, wait a minute, J108 equals J377L. The J is canceled. Can we get what L equal to? 108 divided by 377. Which is 0.287, about 0.3 Henry, approximately. So once actually I know what Z is, I can tell if it's capacitor or inductor if I know what the frequency is. So that's what each one of them is. Now the question came up, why is it square root of 3? And I said, take any two numbers. Because if you have current here, let's say going this way, of some magnet piece value with angle 0, I'll make the math easy. A, this is B here, this is C, and this angle will be negative 120, that'll be, and this angle will be what? Negative 240. Why is this current? Well, if we do KCL at that node, if I define this way, if I do KCL at that node, what do we have? The current going in, I, should equal I sub P angle 0 minus I sub P angle what? Negative 240. Because I define it going in. KCL at that node. The current going in should equal this minus that one. I can factor I sub P out, and what's left? 1 angle 0 minus 1 angle negative 240. Let me go to my calculator here. Let's do the math. Can you see it? 1 angle 0 minus 1 angle negative 240. Look at that, 1.73. What is that? Isn't that the square root of 3? And look at the angle, negative 30 degrees. So the value of that is going to be, whatever I sub P is, doesn't matter, It's going to multiply by the square root 3 angle negative 30 degrees. So whatever this one, the magnitude will be the square root of 3 I sub p, and for the angle, it's going to be whatever theta you subtract from it, 30 degrees. So that's why when they were asking for the magnitude, I said, you know what, I'm not going to go through this math. I know it's going to be that. It's going to be the square root 3 times the value of this. So if I know this guy, I can multiply it by the square root 3. I have that current going in. But that's the result of KCL. So what'd you come up with that equation? Well, the current in equals the current out. Current in is this one, 240, equals the current out, which is what? And if I move that piece there, you end up with that equation. So I didn't reinvent the wheels, I just used KCL. KCL at A. Now, our book tries to summarize what we have. If you have a Y load and phase voltage, here we go. They try to give you what the answer is going to be. We can actually derive them. But it says if you have a Y load, you know VAN, that's the load here, capital A, see that, capital A? VAN, then VBN is going to be 120 off that number, and this is 120 off this one. That's where the 240. What is AB is going to be? Obviously, they're using here positive sequence. See the positive sequence? So we multiply by the square root 3 and add 30 degrees. VBC, again, subtract 120 from that number, which is negative 90. VCA, subtract another 120 from this, and that's where the 210. Now, what's the current I sub AA? If they're Y load with Y source, you just divide them. And that's what you're going to have. On the other hand, if you have a delta here, VAB, the source is going to be between A and B is the square root of 3 times VP, and we add the 30. That's what we got here. And the other one, subtract 120, subtract 120. And once you do that, you convert the source here, then the voltage across the load is really the same thing because they're in parallel there. Same as this. You got a Y to a Y. And the current will be this one, and there's the value for that. Notice negative 30 degrees. Amazing, we just got negative 30 when we did the math there. Remember that? To get what the I sub A, we say it's going to be the square root of 3 times the value, and you're going to subtract negative 30 degrees. That came out from this one, when I just finished with the math. Square root of 3, negative 30. So they try to summarize all of it. So now let's look at delta sources. Mix and match. This actually with the power, if you look at, again, if you look at some of these companies as you're driving by electric company, you'll see the wires coming out. But that's really what you're looking at. Pictures like these, 3-source system. That's the Y. And you have 3 wires coming out of it, A, B, and C. I'm going to go to the end of the book and take a problem and see how we're going to tackle it, mix and match. Try and get one. If not, okay, there's one. I like this one. Hopefully you have some numbers for it. For the balanced 3-phase system, can you see that picture here?
Yeah, I see.
Yeah. For the balanced 3-phase system shown, it is determined that 100 watt is lost in each wire. 100 watt is lost in each wire. That's in the wires. If the phase voltage of the source is 400 volt, the phase voltage, that's VAN, VBN, VCN, and the load throws, this is the load, 12 kilowatts combined, power factor 0.83, determine the wire resistance RW. I like that one. So let me take that and tackle that problem. I'll try to draw it the way they drew it. It's nice, they did a good job with it. I never drew the AN like this. I always try to make them look like a Y. This is A, this is C, and this is B. And this is N, and is attached to, there's a wire, R wire, that's what RW, the wire.
The biggest mistake people can make when you're drawing these is
Too
putting,
high?
huh?
They make it too high, there's no room to go.
That and then also the plus or minus
Yep.
can get flipped.
The minus always with the ground, with the neutral, that's your ground.
Yeah.
So this is C. This is B. And this is A. I forgot to stick a wire here, resistor, RW. And now we're going to go to the top here, that's the A. RW. Now I could actually cheat and use circuit 1 here. I could pull the information from circuit 1. And when you have a balanced system like this, if the values are equal, it's really straightforward. Let's see. Maybe I'll do that. I'm going to convert this load from delta to Y. I can use the equation from circuit 1. In place of R sub 1, R sub 2, put Z1, Z2, Z1, Z2, and Z3. So here we go. Let's make one from delta to Y. And I'll use Z's here.
Are you just redrawing the ZZZ?
Yep. And I'm going to call them Z1 instead of Z, Z2 and Z3. So I'm going to give you an equation for any value, even if it's not balanced. Z1, Z2, and Z3. I'm going to call this value Zx. I'm just looking at my notes from last semester. Zy and ZZ, X, Y, and Z. So I'm using these notes from last semester. I'm just changing the R's to Z's. So this is delta to Y. Zx equals Z1 times Z2. If you remember, the ones are surrounding it, this times that over the sum of them. And Zy, the ones surrounding that, 1 and 3. And Z is, that's this one, the surrounding Z2 and Z3. We were lucky here because why? The values were equal. if the values are equal, that means Zx is going to equal to Zy is going to equal to Zz, which is what? Z times Z over what? Z plus Z plus Z, that's 3Z. And what do you have? Z over 3. So if you want, you can convert actually that to a Y load. And you'll have the value. And you can do the same with this one too. You can go from, if you have the Y and you want to go to a delta, we can use that. And if you do the math from Y to delta, if they are equal, just think about this. If each one is Z, that's Z squared plus Z squared plus Z squared, which is what? 3Z squared divided by Z, that's 3Z. So Z1 equals Z2 equals Z3, which is 3 times Z. So a lot of times when you look in a circuit book, they go Zy equals Z delta over 3. Or you look at this, you go Z delta equals 3 times Zy. It's the same equation when they are equal, when they balance. So you can do it that way. Again, going back to circuits 1 and using these notes. Let's go back to my question, because I forgot what the question is.
It was a long question.
Yep. I drew the picture. It was determined that 100 watt is lost in each wire. So we lost 100 watts here. We lost 100 watts here. And we lost 100 watts here. Each wire. If the phase voltage of the source, that's VAN, it's 400 volts. Was it 400 volts? Yeah. When they say 400, they make an assumption like 400 angle 0 volts. And I bet you that's RMS. They're not saying that, but they're probably making an assumption RMS. A lot of these problems in RMS. And the entire load here draws 12 kilowatts. That means each one of these is what? 4 kilowatts. 4 kilowatts. 4 kilowatts.
Where are you getting the 4 kilowatts from again?
The whole load's 12 kilowatts.
Oh, okay.
And
So
the
I don't have the question in front of me, so I just never remember.
oh, and the power factor is 0.83. Determine the wire resistance. What's the resistance of the wire? What is the resistance of the wire? What is RW? Well, if I know the current through it, I'm done. Right? What's the average power? For a resistor, power factor is 1. So it's V times I. Right? Or power, talking about this one here, through the wire here. Wire is purely resistive, so it's VRMS times IRMS and times, since that's a resistor, there is no phase shift between the current and the resistor, times the power factor of 1. If I use Ohm's law, I can write that what? V equals I over R, right? So it's I squared divided by R. So if I know what the current going from C to C or A to A, so it's the current from A to A squared divided by R. So if I know what that is,
Then you find the average power,
we can get actually,
or the power across that resistor.
we know the voltage here, right? Or I can use V times I and calculate the power. We know what the power is. The power is given to us to be what, 100? So if I know what that current, I'm done. I know what R is.
So we're trying to find R.
Yes.
Okay, I got confused for a second.
So if I can find the current from A to A, this current, I'm done. I can find what R is. Shut up. Don't vibrate. I remind you of the doctor appointment at 1:30. So if I know what the current is, I'm done. Well, can I get the current? Well, I can find this current by knowing this. Do we know anything else besides, we don't know what the voltage cross, right? We know that's 4 kilowatts. We know the power factor. We're not sure what I is. We know what we don't know the voltage, so we could probably figure out. I can really make life easier on me to find what the voltage cross this. I can convert this source to a delta source. I can find VAB and VBC and VCA. So if I convert this source from Y to delta, and that's probably what I'm going to try to do, my circuit will look like this. Let me draw a little bit nicer. I'll put A on the top. I like A on the top. I'm going to put my source here. This is B here, VAB, VBC. Notice how I drew this, VCA, AB, BC, CA. This is that resistor.
Can you move it up a little bit?
I will. This is that resistor. I'm going to take the load A, Z, B, Z, Z. B is going to B, and there's RW, and C is going to C. There's RW. I probably made the problem a little bit uglier too, looking at it there. So by converting this to that, my problem is not nice. I know what VAB. That's easy. VAB, it's the square root of 3 times VAN. We take theta and add to it 30 degrees, right? No big deal. I know what VN, that was 400. The problem with that, the problem just got ugly. What I'm trying to find is what this current is. I think I made it worse. Because if you take a loop there, look at that current. It's going to come, it's going to split. Some will go that way, some will go this way. When this current comes down, this is here I sub BB. This is going to come up this way, split. This and that. So if to take a loop, that a closed loop, I got to travel this way. See it? But the current here and the current here are not the same thing. So maybe that wasn't the smart move. Everyone see why? Trace it. There we go. There's the yellow marker. Closed loop. Some of the voltage in a closed loop is 0. Can you see the yellow? The problem is the current changing constantly there. That's a closed loop. I know what VAB is. I know this voltage. I can do this, but this current and this current is not the same. Unless I cheat and I go, wait a minute, I know what this current, it is the square root of 3 times that current, an angle of negative 30 degrees. So if I want to, I could do that, whatever this current, if I call this I sub x, this will be the square root of 3 times I sub x minus the 30 degrees. And this is I sub bb, that means this current is going to be what? 120 degrees off that one. So I can write them in terms of that and really solve for the current. I can get that. I can get this current. Once I know this, I can find that one. But I think it might have been easier if I converted that to a Y. I wanted to show you both and see which one looks a little bit nicer. So let's go back. So let's hold on this and see. That's just an idea. Convert the source from Y to delta and end up with delta to delta. What about if I take that source now, leave it alone, but take the load and convert the load to a Y? Let me draw that one again. I'll redraw it just a little bit differently. I'll put A on the top. This is A, this is N, this is B, this is C. Now, let me take the load and convert the load to a Y load. This will be Z over 3. Remember, the reason why Z over 3, we going from delta to Y. From delta to Y, each one of these will be whatever that divided by 3. Now, if I travel in one direction, if I grab a path here and I go through it, if you grab one loop, this is what I see. VAN RW Z over 3, and this is AN. Let's see what we know. This is the equivalent of that. This is equivalent of delta. So each one of these still 4 kilowatts. Power factor equals 0.83 lagging. Each one of these still 100 kilowatts. And the question, can I find what this one is? We know what VAN This is what? Was it 400 angle 0 in the problem? Yep. 400 angle 0. That was given to us. Is there a way now I can figure out RW from this little tiny circuit? So circuit-wise, we shrunk the problem. The question, how would I solve this? I can do complex power, right? I can figure out what the power, complex power of this only real power, combine them, that's the power by the source. What's the complex power by this? And if I know what the power by this one, and I know what the power factor, I can tell you what the current going through it. I can tell you what the value of that current is. Because complex power says what? The power is the voltage times the current conjugate, right? So let's look at this. Complex power. Let's look at the load here. This is what I know. 0.83. What's the inverse? 0.83.
There's somewhere around like 37, 38.
That's the 80's point. Yeah, cosine 0.83. A little bit off because that's 83 instead of 80.
Yeah.
33.9, about 34 degrees roughly. We know the real portion of that. We know this is 4K, 4,000. Can we get what Q is? So S for the load is equal to the 4,000 plus J, and I need to figure out what that number is. I can do it by doing trig. Tangent 34 degrees equals the side that's opposite over the adjacent. Q equals what? Take the tangent of that, multiply it by 4,000. 2688. How about 2700? We'll just make it. As for the wire, it's 100. That's a lot of power, huh? Was it 100 kilowatts or 100 watts? $100. I was like, wow, we lost a lot of power. Not kilowatts. Because the whole thing is 4 kilo. To lose here 100 kilowatts, you're in trouble there.
So really bad.
Yep. So 100. So now we add them. So what is S total here? Is what? 4,100 plus J 2,700. Which we can get the magnitude of that. The magnitude of that is going to be what? 4,100. So let's take that number. By the way, I'm carrying all that 2688. I'm carrying all of them instead of 2,700. So my number might be a little bit off there. Plus 4,100 squared. So we take the square root of 4,100 squared plus 2,700 squared. We can get you the angle if you want to. We can get you the power factor.
Wait, why are you getting the square root?
That's the magnitude.
Oh, right, because it's
Yep.
the triangle, right?
It's 4902. And if you want the angles, you know what the power factor, second tangent, roughly 2,700 divided by 4,100.
Where did the J go when we squared it?
You don't, you just take the magnitude, this one squared, that one squared.
Oh, right, okay.
So the angle is 33.4 degrees. So really the power factor equals cosine 33.4 which is 0.835. I'm sure rounding errors affected that a little bit there.
How did you get the angle 33 point?
Inverse tangent.
You did the
Inverse tangent, yep.
of 4902?
This one.
Oh, that, okay.
You have 4100 this way, 2700, 2688 actually, and that's what theta is. So what you found is S total, which is that number, which is this one squared plus that one squared, and theta is the inverse tangent of those numbers. And if we go back to the previous chapter, the last thing we did, complex power, was it chapter 11? I'll put that equation quickly here. What is complex power? Complex power. When we start talking about complex power, here we go. It's the VRMS times the current conjugate. So you can figure out what the value is. The magnitude of that, if you just want the magnitude, that's apparent power, actually, absolute value of that. Volts, amps. So V effective, I effective, theta, that's what the complex power. Well, if my voltage has 400 angle 0, so this is roughly, we said 34 degrees, right? So I know the complex power now. As for the source, is equal to what? I said 4902 angle roughly 33.4 equals the voltage cross, the voltage is VAN, times the current going through that conjugate, times the current through this, which is the same current through that one. (4902) angle 33.4 equals 400 angle 0 times I sub AA conjugate. Do we know what I sub AA conjugate? 4902 divided by 400, which is 12.255 angle 33.4. So what is I sub AA without the conjugate? 12.255 angle negative 33.4. So that's the current from I sub A to A. Remember earlier I said I can find R if I know what the current is. I can use this equation. So here we go, 100 equals I sub AA, the magnitude of that, over R. 100 equals 12.255 squared, no angle, over R. Square that, divided by 100. Guess what R is? 1.5 ohm.
So you don't need the angle when you do 12.2.
Nope, because that's the magnitude. Yep.
Because you're just getting the magnitude.
Well, it's cosine theta V minus theta I is going to be a 0 there. Because that's all resistors. There's no
right.
shift. There's no difference between theta V. Notice when you only have a resistor, if you know the current through it, the voltage is that resistor times the current. So the angle itself will be the same. That's why the power factor is a 1. Theta V minus theta I is 0, cosine 0 is 1. So it's the magnitude times the power factor.
Okay.
So that's the value of R, which is 1.5 ohm.